dying. Everybody's dying, like, because no one does that, but apparently they still do, even at 31 years old. Okay. Here we go. So we know that 3, base 3 and log of base 3, exponentials undo logs, logs undo exponentials, right? Base 3, log of base 3 of 10. 3 and log of base 3 cancel out, we get 10. That's what she said in calculus for students who are having a hard time with and forgetting. So don't forget that. Now ln and e are just exponentials. There's a natural log, which is the special exponential. Ln and e just undo each other. Exponentials undo logs, logs undo exponentials. So our answer was 2. So pretty straightforward here. All right, so I just want to go over this really quick, this problem. You were asked to kind of graph this in the book, and I just want to kind of talk about this one. Because we should be able to think of this without graphing it first. So I just want to make sure we can kind of think this through without graphing it. So our vertical asymptote, guys, a non-shifted log would be this. Log to the base 3 of x, correct, everybody? Don't those type of logs have vertical asymptotes at 0? So let's figure out where the shift is, and won't that be our new vertical asymptote, where our shift is left and right? Yeah? Does everybody understand? So let's set this equal to 0, because right now it would be at 0. So let's set 2x plus 4. So if I said to you, do not graph and tell me the vertical asymptote. So you would set that equal to 0 and solve for x. So we would subtract 4, negative 2x equals negative 4 divided by 2. So x equals 2. So now that's been shifted right to, correct everybody? Is everybody good? So that would be a vertical asymptote at right 2. So x equals 2 is our vertical asymptote. Our x-intercept, we should just be able to solve using algebra. So the moral of this is being able to do this without a graph. You see what I'm saying? Okay, so our x-intercept is when, for all functions, is when y equals 0, isn't it? Guys? So we have 0. I'm going to do the algebra down here. 0 is equal to log the base 3 of negative 2x plus 4. And now let's use algebra to solve for x. So how do we undo? X is trapped inside the log. How do you undo log to the base 3? Good. Base 3 of both sides. 3 to the 0 power is 1. I'm going to scroll up real quick. So we have 1 is equal to log the base 3 and base 3 cancel out. Negative 2x plus 4. Now let's use algebra to solve for x. Subtract 4 from both sides. Negative 3 equals negative 2x. Now divide both sides by negative 2. So x is equal to 3 halves. Algebra versus graph. Okay, so now our x-intercept is technically a point. We get 3 halves, comma 0, correct? So that's going over 3.5. Oh, what? 1.5. Guys, 3 halves is 1.5, right? And on 0, that's where it's crossing the x-axis. Our domain, this is the big one. You're going to be asked in calculus, what's the domain of this? Now think about it, guys. The domain, won't that be, if it's non-shifted, 0 to infinity? Or wouldn't we be able to say x for non-shifted, log the base 3 of x, wouldn't we say x is greater than or equal to 0? Right? So what we're going to do is we're going to say negative 2x plus 4 must be greater than 0. Oh, I said equal to 0. Because that asymptote, is it ever going to be that asymptote? No, so I need to go up and erase the or equal to. Do you guys get what I'm saying? So we would find our domain using algebra this way. Negative 2x plus 4 must be greater than 0 because we're looking at where's our shift now. Do you get what I'm saying? Because our original non-shifted one has a horizontal asymptote of 0. So, and remember what log looks like this, right? So we know that our original domain would be x values larger than 0. So now we've shifted it. So let's set our shift. Our shift is greater than 0 and solve. Yeah, that's just the original. Yep. So solving for x, we'd subtract 4, negative, just like we've done, but watch, because we've got to be careful here. There's an inequality. Negative 2x must be greater than negative 4. Now don't we divide both sides by negative 2? Did we just divide by negative? Yes. So you have to change the sign of the inequality. So x will be less than 2. Our x values will be less than 2. And that's because this logarithm ends up looking like this. It's a reflection over the y-axis. That's what a negative does when you plug it in front of x versus over here, right? Negative out here is a reflection over the x-axis. This is a reflection over the y-axis. So do you see how it was reflected over the y-axis? Okay, so this is what our graph looks like, so the domain makes sense. X value is less than 2. But I wanted you to be able to find the domain without graphing it. So do you get where I'm coming from with this, everybody? Okay, because I just didn't know if I didn't think I went into enough detail last time about that. Okay, awesome. Okay, let's get to 7-3. This is literally one of my most favorite lessons. It's super fun. Love it. So today we're going to be doing properties of logarithms. This is a huge thing. We did learn some basic properties of logarithms last time, but now we're learning all of the properties of logs, which are super awesome. So recall, an exponential is the inverse of a log, and a log is the inverse of an exponential. So to rewrite base 5 to the third power equals 125 as a log, just a reminder, we would do log to the base 5 of both sides. Log to the base 5. So those cancel out. So 3 is equal to log to the base 5 of 125. Now, I wasn't very clear with this class. Do you guys all understand that that entraps 125? Like, there's parentheses around that. It's not multiplied by 125. Like, it entraps it. It's log to the base 5 of 125. You get what I'm saying? It's not log to the base 5 times 125. So I just need to make sure I was clear with you guys. As in, if we write a logarithm, it's log to the base b of x, like that. Because what it really means is the exponential. You know what I mean? We can rewrite it, but we're about to do an example. So log the base 16 of 8 equals 3/4. So what does base 16 mean? Well, let's figure it out. How do you undo log to the base 16? Base 16 of both sides, right? Yeah. So log base 16 cancels out. So 8 is equal to 16, base 16 to the 3/4 power. So it's just saying that we have an exponential of base 16. Like you can rewrite an exponential as a log and a log as an exponential. Okay, so let's rewrite this as an exponential. ln, what undoes ln? E, so we have base e of both sides. ln and e undo each other. So 4 is equal to e to the 1.386. Okay, perfect. What undoes base e? We're going to go put it back into a logarithm. ln, natural log. ln and e undo each other. So 2 is equal to the ln of 7.3. Everybody good? That was just a review of what we learned last time. Okay. Okay, so then also remember that log to the base 10 will have the form nothing there. So y is equal to log of x really means base 10 of x. It's just, it goes without being said that there's a secret 10 there. Now, most calculators, not all, but most, and I'm telling you, I learned calculus 1, 2, and 3 without even touching a calculator. You need to be able to do this. So even if your calculator does have this option to be able to quickly do it, learn the change of base formula. Okay, so I just had to say that because people always are like, I don't need to learn that because my calculator will do it. Okay, so here's the change of base formula. So most calculators, like my TI-83s over there, they only have 2 types of logs. They can calculate log to the base 10, so just log, and then also the natural log, also ln. So if we have log to the base a that is not a 10 of x, we still need to be able to evaluate it. We still need to be able to type it in and find the approximate value of that. So we want to be able to do that using our calculator, but once again, our calculator only uses base 10. So you can literally rewrite this log to the base a of x as base 10 by rewriting it as such. Log of x, so this is really log to the base 10 of x divided by log to the base 10 of a. So you can take this and rewrite it in this form, and they're equivalent. So here's one thing that I like kind of help people, like a trick to help you remember. See, you know how this is like small? When I say small, I mean like this little guy is like small, like a little sub down here. So this is the small thing, this is the bigger in size. Not bigger in number, but bigger in size. So you always, to rewrite this in base 10, you do log of the big thing divided by log of the small thing. Not small in number, but small in size. Does that make sense? Like literally this is smaller in size. So you do log of x over log of a. And now we can type it into our calculator because it's base 10. So you can type into your calculator log of this divided by log of that, and you will get it right. So that also is true for ln. If you have ln of If you have L, you can rewrite it as ln. So you can, instead of writing it as a log, you can write it as a natural log. ln of x divided by ln of 8, and you'll get the same answer. Your calculator will give you the same answer. Do you guys have your calculators out? Do you see what I'm saying? Look at your calculator. Right here. Log. So if you go to, just like right here, like for example, log, notice it's just base 10. So do you see why that's a problem? Okay. All these logs have different bases. So for example, right here, it says log the base 4 of 25. Now I want to make a connection here because this is what a lot of people get confused on. We could try to evaluate this how we've been evaluating it the past few times. Remember that I said evaluate that and we just set it equal to x and rewrote it as an exponential, right? So then we did base 4 of both sides. That canceled out with that. So we have 4 to the x equals 25. 4 to the first power is 1. 4 to the first power is 4, correct? 4 to the second power is 16. 4 to the third power is not 25. So do you see how it's not a pretty number? Like it's nothing pretty. It's not an easy answer. You get what I'm saying? It's not a perfect solution. So we would not evaluate it this way. So this is when we would, instead of evaluating it by putting it in exponential form, which was hard because there was nothing very straightforward, that was our answer, we're going to use the change your base formula to rewrite this. So how we could do it is put it in base 10 using the change your base formula. So we can literally rewrite this as log of 25 divided by log of 4. So log of the big thing, big in size, divided by log of the small thing in size. Now we can type that into our calculator because it's base 10 now. So type in, and let me show you what you have to make sure to do. So do log of 25, close your parentheses, divided by log of 4. Hit enter. So we would have never got that decimal. Like we would have never guessed that by putting it as an exponential. Now watch, we can even check that though. We can check it because it is an exponential. So here's our exponential, 4 to that decimal equals 25. So let's look. 4 raised to the second answer, so that puts in the decimal. I'm going to check my answer. 25. That truly was the decimal that worked for us. So we would put out, if we were solving or anything, we would use the full decimal, but in our instructions, I think it does say round to 3 decimal places or whatever. So 2.32. But when checking it, you'd want to put in the full decimal. Questions on that? Okay, awesome. So watch how cool this is. If you do the natural log instead of log, so we can also rewrite this as ln of 25 over ln of 4. Type that into your calculator, and you get the same decimal. Perfect. 25 divided by ln of 4. So you can use either, but I just usually use log, unless it's e. Oh, yeah. Then it was supposed to be 25. Okay, perfect. Well, it is the same, so we got it the same, right? Okay, perfect. Okay, awesome. So let's do another one, and then we're good for a minute. So, log the base 2 of 12. I showed you, look, I did try first to rewrite it as an exponential, but then there's no easy answer here, because it's not 2 to the first, it's not 2 squared, it's not 2 to the third. It's like, okay, it's got to be a decimal then, so it's not a pretty answer. So that's when we'll just solve it using the change of base formula. In fact, now that I know the change of base formula, I almost use that most of the time. So we can rewrite this as base 10 to our calculator as log of 12 divided by log of 2. Or we could do ln of 12 divided by ln of 2. So type that into your calculator. What's the decimal? 3.5. And then if you were going to check it, was it exactly 3.5? Okay, but if you were going to check it, you would just type in your full decimal. You do 2 to the entire decimal, hit enter, and it will equal 12. Okay, perfect. So this is the next thing. This is the big whammy schwammy for today. These are properties of logarithms. So write these down. Or take a picture. Either one will work great for me. So these are properties of logarithms. So you know that logs can be written as exponentials because they are inverses of each other. So properties of exponents will also hold true for properties of logs. They go hand in hand. So remember back to when we were doing properties of exponents. That means like when you have the same base, like 2 to the third power times 2 to the fourth power. When you multiply, you add, right, everybody? So that would be 2 to the 7th. When you divide, let's say we had 2 to the third divided by 2 to the fourth. When you divide, then you subtract the top from the bottom, right, everybody? So that'd be 2 to the third minus 4. And then properties of exponents, right? Bases, same base. When you multiply, you add. When you divide, then you subtract. Raise a power to a power, and you multiply. Very good. Those properties of exponents also hold true for properties of logs. So everybody look. Log to the base A of u times v. When you multiply, you add. So we can take this and split it apart and rewrite it as log to the base A of u plus log to the base A of v. So they still have the same base A, but because they were multiplying, they're adding. Now, really, it's more beneficial for us later on. The reason we really learn this is to be able to actually go backwards, to be able to take this and say when you add, you multiply it and put it into one logarithm. That's really more what we're going to be going for a little bit later on. So you have to be able to go back and forth. So same with ln. ln of u times v can be split apart and written as ln of u plus v. So if you have ln of u plus v, it'd be more beneficial to put it together as one ln and do it as u times v. When you multiply, you add. When you add, you multiply. So then the quotient property, log to the base a of u divided by v. When you divide, then you subtract. So log to the base a of u, the top, minus log to the base a of v. And once again, so if we see subtraction, we would want to put it back together as one logarithm. So we would do u divided by v. Yes. Good. It does have to be logged to the same base to be able to go backwards and put them together. Otherwise, you have to keep them split apart. Good question. Same with ln. Rule still the same. Now, here's the raise a power to a power, and you multiply. It is multiplying. Notice they're taking the n and pulling it out and multiplying it in front. You're always going to see me draw this and go and pull it down. It's multiplying in front. So raising something to a power n, you multiply. So that comes in front and is multiplied. Power is multiplied. So then going the other way, I'm just going to scroll up a little so it doesn't look bad. So then going the other way, so once again, we're taking this, we're raising power to a power, so we multiply. We put it in front. So it's really more beneficial for us. The whole point of learning this is so we can go the other way, taking this n and putting it up here as an exponent. Now that's only if it's multiplied in front of the log. Everybody good? Yes. Yep. No, just u to the just the what's inside here. Anything that's inside the logarithm will be up here. Good question. All right, we have those written down. Now it's just fun. This is the fun stuff. Let's start practicing. Okay, so it says write each in terms of ln of 2 or ln of 3. So notice, this is ln of 6. Isn't this to be written as 2 and 3? Couldn't we rewrite this as ln of 2 times 3? So it wants us to take the ln of 6 and rewrite it in terms of ln of 2 and ln of 3. Does everybody understand the instructions? So you're just using your thoughts, like, oh, hey, you know, I could rewrite 6 as 2 times 3, couldn't I? Okay, now let's keep splitting this apart. When you multiply, you add. So this is, now we can split this part into 2 ln's. ln of 2 plus ln of 3. And we're done. So we split it apart. We are using our creativity. Yes.
How does that help you?
It doesn't. This one's just getting us practicing. So we're going to learn how this helps us later. Right now we're just saying, let's practice the properties. So what this ends up helping us with, I'll tell you, is going the other way. Given this, going backwards so that you have one ln, and then you can solve equations if you have one ln. Okay, so let's do this one. So ln of 2 divided by 27. It wants it all in terms of ln of 2 or 3. So can anyone think of how we could rewrite this? Yeah, 3 to the third. You're absolutely right. So this is ln of 2, very good, divided by 3 to the third power. Way to think of that. So now let's split it apart. So, first of all, when you divide, then you subtract, you always subtract the top from the bottom. So we're going to have ln of 2 minus ln of 3 to the third power. Now, one last step, we would never leave that, if we're going backwards, we would never leave that exponent up there. We're going to take it and pull it out in front here. So we would have ln of 2, because we're raising a power, some base to a power, so we multiply. So it would be written as minus 3 ln of 3. And that's how you'd rewrite it. So that's, if we were going backwards, we'd pull this up into our exponent and then divide them. Put it in 1 ln. So now we've rewritten all in terms of ln of 2 and ln of 3. Okay, so it says find the exact value without using a calculator. So this is where it's also beneficial to use properties of logs. So looking at this one, we have log to the base 5 of the cube root of 5. So let's rewrite this in a better way so that we can maybe simplify. Because don't we know that log of 5 and base 5 cancel out? Right? So let's rewrite this. Isn't this the same thing as this? Log the base 5 of 5 to the what power? Good, 1/3. Very good. So now, log the base 5 and base 5 cancel out, don't they? Yes. So our answer would have been 1/3. So we had to do a property of logarithms first to be able to cancel those out. Yep, that is what it simplified to be. Yep, good question. So looking here. We have ln of e to the 6 minus ln of e to the second power. We have 2 ln's split apart. So we're going to want to put this into 1 ln so we can simplify it. Okay, there's many ways to do it. Yes, it is going to be 4 because ln and e cancel out. So we get 6. And then ln and e cancel out minus 2, which is 4. Very good. Sorry, I was thinking about something else. Okay, so let's see if that comes out the same as using properties of logs. So when we subtract, we divide. So we have ln of e to the 6 divided by e to the second, right? Putting it into 1 ln. Do you see what I'm doing here, everybody? This is the hard way of doing it. This was the easy way. So now when you divide them, you subtract. So this really is ln of e to the 4th, right? ln and e cancel out, we get 4. But this was way quicker and easier. So why make it harder? But it's good to see it both ways. Okay, here we go. Expand the logarithm. So you've got to decide here what's going on. It's all multiplication. Now understand 5 is its own base. It's not connected to x cubed. So we're going to think of this as such. It's all log to the base 4, so we're going to split it up. When you multiply, you add. So we would rewrite this as log to the base 4 of 5 plus log to the base 4 of x cubed plus multiplication, right? You see how I'm just splitting it up, guys, and putting it in the different bases? Yeah. Plus log to the base 4 of y. Now from here you'd say, is that an acceptable final answer? Well, no, because we have an exponent. Exponents will always be fixed by pulling them and putting them in front. Raise something to a power and you multiply. So we'll put that 3 in front. So we would have log to the base 4 of 5 plus 3 log to the base 4 of x plus log to the base 4 of y. So it's splitting it apart so that we can more easily put it together. Because there is not a whole lot of point to splitting something apart. You'd rather have it together. But it's this that helps you easily put it back together. Seeing this. That's the point of doing this. So let's do this one. It says expand the logarithm. You've got to go in the correct order here. So this one we're going to have to think about a little bit. So we have ln of all that stuff. So I'm going to rewrite this as ln of, anytime I'm dealing with radicals, isn't that really just exponent? Like a fractional exponent, remember that? Yeah. So this is really ln of 3x minus 5 all to the 1/2 power. And then that's divided by 7. So now when you divide, you subtract. So we can split this apart. So we have ln of 3x minus 5 to the 1/2 power minus ln of 7. Does everybody understand? Then one more step would be taking the power down. So we grab the 1/2 power, pull it out in front. No, we're not solving yet, because there's no equal sign. So what we're doing is we're getting ready to be able to solve. Because what will happen is they'll give you an equation that's all split apart like this. They'll write it. So this is, I'll explain right here now. So let's finish splitting this apart. So we pull the 1/2 down in front. 1/2 ln of 3x minus 5 minus ln of 7. That would be our answer. We're just pulling it apart. So the reason we're doing this, guys, is because then what if I gave you, change the problem, which you're going to see in the future, and I said is equal to 8. So now we're solving for x, correct? Yeah. So we've got to get x alone. Now because of subtraction, we can't undo ln unless this is 1 ln. Otherwise we'd be breaking the forbidden rule. You know what I mean? You can't just base this. Like you have to have 1 ln to undo it. So we have to put it back together, Sarah, and then undo ln. Does that make sense of why so that you see why we're going with this? Okay. We're separating it so that eventually, here's why. I'm telling you, I've taught it in the past, where I just teach the other way of starting here and saying put it back together, and people get completely lost. So once you've seen it split apart, it's much easier to go backwards. Yeah. It's a method of teaching. Okay, so now here's the thing. Here's what it would get. This is where it's, so if I want to show that first, this is where people have a really hard time with. I start here. If I say to you condense the logarithm and you haven't seen how to split it apart, it's a lot harder. So now we know when you add, you multiply, right? Yeah. When you have something in front, it's really an exponent. So that's what we're going to fix first. So now the point is this, really being able to go this way. We have 2 logarithms that are both base 10. So we want to make this one logarithm. Let's go backwards. Pull the exponents up. That's our first step. So we would have log of x to the 1/2 power plus log of x plus 1 to the 3rd power. I'm going to do it in steps. When you add, you multiply, right? So here we go, writing it as one log. Log of x to the 1/2 times x plus 1 to the 3rd power. And that's all trapped inside the log, right, everybody? Yeah. Okay, perfect. That's all we got to do. And now if it had equals 10, now we can undo log by base 10ing both sides and then solving for x. Yes. But we would not be able to do that up here because of the addition sign, you can't just base 10, base 10. Yeah, good question. Okay, here we go. Condense the logarithm. So the first thing we would do is say, I need to fix all the exponents first. Ding, ding. That's got to come up. Looks like that's it. So we have ln of x plus 2 squared minus ln of x. So they're both ln's. Our goal is to put this as one ln. So we're going to have ln of, when you divide then you subtract. When you subtract then you divide. This divided by this, right? So x plus 2 squared divided by x. We've now written it as a single logarithm. And so yes, if now I put in equals 10, you would say, I can solve this now. Base E, solve for x. It doesn't. I was just showing you once again the example. So we were stopping at that. I was just making sure you understand the point once again. We're about to get there. Okay, perfect. So condense the logarithm. So this one, we're almost there, and I'm going to let you just go for it. Like literally, like this is the end of the lesson here. So, condense the logarithm. So notice this one is very interesting because notice the 1/3 is multiplied to all of that, correct, everybody? So let's go ahead and rewrite it. Let's distribute it. So it'd be 1/3 log to the base 2 of x. It's this times this, right? Plus 1/3 log to the base 2 of x plus 1. So now we would fix our exponents. So we have log to the base 2 of x to the 1/3 power. And then plus log to the base 2 of x plus 1 to the 1/3 power. So now from here, when you add, you multiply. When you multiply, you add. So this is log base 2 of x to the 1/3 times x plus 1 to the 1/3. So wouldn't it be prettier, let's think about it, wouldn't it be prettier, since they're both to the 1/3 power, to say log the base 2 of x times x plus 1 to the 1/3 power? Yeah. Okay, that would be the final way of writing it. Just making sure you write your answer in the most pretty form possible. Okay, let's see here. Yeah. Making sure we all got this all good. Yep. Perfect. That is literally everything. So it's just practicing those, making sure you get them right. Yes. Good question. You know, actually, it really, I mean, they mean the same thing, so they're both right. I see what you're saying. We would probably even go as far as to, we could go as far as to write the cube root of x times x plus 1. And it honestly depends on the pre-calculus book on which answer they're going to put in the back of the book, because not one is more correct than the other. But I'm assuming this book's going to go this far. Does everybody understand what I'm saying? That's usually what they're going to rewrite it as. Well, they're both equal in value, so I probably will just say, hey, why don't you rewrite that as a radical? Good point. Let's do that. Do that. This would not be wrong. Do you get what I'm saying? Aren't those the same thing, guys? Yeah. But I do think that this would be smart to go this far, because usually this is what you're going to be seeing going the other way. But really, they're equal in value, right? Okay. So not one is more correct than the other. They're the exact same thing. So I can't say one is more correct than the other, but I will probably suggest, hey, rewrite that as a radical. So like on this, what's there another one? No, I probably wouldn't mark it wrong. I mean, I wouldn't mark it wrong, but I might say like, hey, rewrite it as a radical. So look right here. I probably am going to push you though, since this is like technically a radical, even though they're the same thing, to rewrite it as such. Just because if you were going backwards, this is what you'd be seeing. Does that make sense, everybody? So yes, from now on, if you have a fractional exponent, just quickly change it to a radical. Same thing though. So I can't say I would mark it wrong because it's the same thing. It's hard. I'll ask Mr. Roberts what he thinks, but it's not wrong. So they're literally equal in value. Okay, go for it. So that looks like a lot of problems, but it's really because you need to practice that many. And really, you're going to get done with them in class today because you're going to come back from lunch and just go for it. Sweet.